afternoon. I hope you have enjoyed the few days of vacation. And now you should be able to see on the screen a page entitled Hamiltonian Operator 3. And this is the last exercise that we are doing. From tomorrow, we shall start again with the material that is the exam. The exercise of today is related to the solution of the Schrödinger equation independent of time in a periodic potential energy, because it is a typical case that occurs in crystals. You remember that crystals are periodic structures. If we assume that the atoms are fixed in the equilibrium positions, then the force felt by an electron that moves inside the crystal is due to a potential periodic energy. So the force itself is periodic. Of course, the form of the periodic potential energy is very complicated. But we shall take a very simplified model that is so simplified that allows us for an analytical solution. However, many important features of the actual solution are kept by the simplified model. In this page, there is nothing that you have to learn, because it is simply a reminder that in a periodic structure like a crystal, you have translation vectors that are called L. They belong to the direct lattice, and they are linear combinations with integer coefficients m1, m2, m3 of the characteristic vectors of the lattice a1, a2, a3. So in order to describe the periodicity of the potential energy V, we simply write that V of any position R plus L, with L any translational vector of the lattice, is equal to V of R. That is the expression that describes the periodicity. You also remember that we associate a reciprocal lattice to the direct lattice, and then we associate a scaled reciprocal lattice to the reciprocal lattice. And the scaled reciprocal lattice has three characteristic vectors that are, as you remember, 2 pi b1, 2 pi b2, 2 pi b3. Okay, each vector b is obtained by taking the mixed product of the A vectors and dividing the result by the volume of the cell of the direct lattice. So any vector k in the reciprocal scaled lattice is made of a linear combination that you can see on the screen, a linear combination of the vectors 2 pi b1, 2 pi b2, and 2 pi b3. In principle, the coefficients of the linear combination should be real numbers. Okay? But you remember that at some point we introduce the periodic boundary conditions. And the periodic boundary conditions have the effect, one, to restore periodicity in a finite volume of the material that in principle is not periodic. And number two, the second effect is that when we impose the periodic boundary condition, the coefficients of K become discrete, become ratios of integers to other integers. So the numerators are the small n1, n2, and 3. And the denominators are capital N1, capital N2, capital N3. So N1 is the number of cells of the direct lattice in the direction of the first axis. N2 is the equivalent in the direction of the second axis, N3 is the equivalent in the direction of the third axis. The numerators, small n1, small n2, small n3, are integers that go from 0 to capital N minus 1. And this is again due to the periodicity. That means that we can limit the consideration of the K vector only to one period of the reciprocal scale lattice, and this period, as you may remember, is the elementary cell. And in many occasions, we use for the elementary cell the Brillouin zone. Okay. And the second consequence is that the total number of distinct K vector in the Brillouin zone is capital NC, that is the product of N1, N2, and N3, and is also the total number of cells of the direct lattice. That means in practice that the K vectors, although discrete, are many. They're very dense, okay? So that when we take derivatives, we can do it safely because the variation of K is in any case very small. Okay, so we can take the derivatives with respect to K even if in principle K is discrete. Okay. Now, in order to try an analytical solution of the Schrödinger equation, we must introduce a number of simplifications. But before starting with any simplification, we can also exploit another result that is fully general. So there is no approximation involved for the moment. And this result is that when we want to solve the Schrödinger equation, when the potential energy is periodic, we find that the solutions have a special form. And this is a very general theorem that applies actually to operators that are periodic. And the Hamiltonian, you may check it immediately. If the potential energy is periodic, then the full Hamiltonian is also periodic because the kinetic part is invariant upon translation because there are just the derivatives. Okay, so if you take a position, you add a vector to the position and then you take the derivative with respect to position, the added constant disappears. So the kinetic part is intrinsically periodic. If the potential energy is also periodic, then the complete Hamiltonian is periodic. Then, when the Hamiltonian is periodic. We know from a theorem that should be somewhere here that the solutions of the Schrödinger equation have a special form. If it is not in the previous pages, we shall meet it somewhere below, okay? We shall do it in a minute, okay? So now we have to introduce the simplifications that make it possible to solve the problem analytically. And so we take the simplest possible form of a periodic potential energy, that is something, as you can see in this figure, something that is piecewise constant, okay? So we take a one-dimensional situation first, and then we assume that the potential energy that is periodic has the form of a succession of barriers of potential energy like those that you can see in the figure. In other terms, the potential energy is zero over some intervals, and the extension of this interval is a, small a, as you see in the figure. And then the potential energy in the other intervals, whose width is equal to b, is non-zero, has a constant value that is called V0, okay? Next, we consider a situation in which the energy of the particle is given. So we assume that the particle has an energy, a total energy equal to E. And for some reasons that we shall see later, we may start considering that E is smaller than V0, okay? In fact, later on, we shall take the limit in which V0 becomes very large, okay? So it is sensible to consider E smaller than V0. Then the point is we have to solve the Schrödinger equation. Obviously, the period of the potential energy is A plus B. So the potential energy is periodic with the period A plus B. Okay. In principle, what we should do, you remember we have done this on simpler cases before. What we should do is that we solve the Schrödinger equation in every domain, like A, or in every other domain like B. And then we impose the continuity of the wave function and of the derivative of the wave function at the edges of each interval A and B. Okay, so we should consider infinite solutions and infinite matching condition at the boundaries. Okay, but in this case, because we have to deal with the periodic structure, we shall see immediately that it is sufficient to solve the equation only in one period, okay? And this is due to the theorem that I'm going to introduce in a minute. Now we have to calculate the characteristic vectors of the direct lattice and those of the reciprocal scaled lattice. Obviously, it is sufficient to consider only one characteristic vector, that is A1. Okay, A1, if we take the one-dimensional situation in which the potential energy depends only on the x-axis, A1 is equal to the period A plus B times I1, that is the unit vector of the x-axis, okay? However, we may still think that we are in a three-dimensional case in which the potential energy is uniform in the second direction and in the third direction, okay? This is important because when we have to calculate the reciprocal lattice, we need vectors that are the vector or the mixed products of A1, A2, and A3. So we actually do need all these three vectors, A1, A2, and A3. But we can just take A2 as any number, A2 times I2, and A3 as any number times I3, because we don't solve in the direction of the second axis or the third axis because we have uniformity. We just exploit vectors A2 and A3, okay? So when we calculate B1, you remember B1 is the vector product of the other two vectors with different indices divided by the mixed product of the three vectors of the direct lattice. So we have A2, I2 wedge A3, I3, and then we divide by the mixed product that you can see there, okay? Of course, we assume that A2, A3, and A1 are mutually orthogonal because they are proportional to the unit vectors of the axis, okay? So the vector product in the numerator gives I1. And the mixed product I1 dot I2 wedge I3 gives you 1, the unity, okay? So in conclusion, after simplifying A2 and A3, we have that B1 is simply equal to I1 divided by A plus B. Then we can calculate also B2 and B3, but they are not used anymore. I have one point that if any of you has the paper version of this page, there is a misprint, okay? Very likely, instead of having B2 equal to I2 over A2 and B3 equal to I3 over A3, there is the same formula repeated twice. It is a mistake, okay, a misprint. Now we go from the reciprocal lattice to the scaled reciprocal lattice, and we multiply each vector B1, B2, and B3 by 2 pi, okay? In this very simple case, the Brillouin zone is just a segment along the x-axis, okay? And the length of this segment is 2 pi divided A plus B. You remember that the Brillouin zone is symmetric with respect to the origin. So one half of it stays on the left and the other half of it stays on the right. So the Brillouin zone goes from minus pi over A plus B to plus pi divided by A plus B. Okay? Now we have to solve the Schrödinger equation, and we do the same procedure as we did for the barrier. You remember, when we have a barrier, we solve separately the Schrödinger equation outside the barrier and inside the barrier. So if we take one of the intervals in which the potential energy is 0, like here, you remember E is larger than the potential energy because the potential energy is 0. And of course, you remember that E cannot be smaller than the minimum of the potential energy, so E must be positive. It follows that the solution of the Schrödinger equation is expected to be oscillatory, and the equation to be solved is minus the second derivative of the wave function W equal, in general we use K, the modulus of K in this case, but we have another symbol, alpha, because K is reserved for another thing. So we have alpha squared times W, and alpha is a positive quantity that is proportional to the square root of energy. This is something that you should remember because we shall use this alpha later, okay? In contrast, when we go to solve the equation in the intervals in which V is equal to V0, then we have that V0 is larger than E. So the solutions are real exponentials, as you remember. And the equation to be solved is the second derivative of W equal to beta squared times W, and beta is the square root of 2m V0 minus E divided by H bar. Of course, V0 is larger than E, okay? So this is just standard. This is something that you have already seen before, okay? But now we introduce the theorem that tells us that in the special case of a periodic potential energy, we know a priori that the solution W of the Schrödinger equation has a special form. And next we are going to see what this special form is. In one dimension, the special form is this. W is equal to another function that we call U times the exponential of jkx. And function U has the property of being periodic with the same period as the potential energy. You remember that in one dimension, the period of the potential energy is A plus B. So this function, U sub k, calculated at any x plus A plus B is equal to U sub k calculated at x. So what is k here? K is the wave vector in one dimension, so it is a scalar actually, okay? And you remember it is related to the expectation value of momentum, okay? So this k vector is a parameter, and in the solution of the equation, we shall be able to connect this parameter with the total energy. So we shall be able to find eventually the relation between total energy and momentum, okay? This theorem that states that the solution of the Schrödinger equation in the periodic potential energy is equal to the product of the exponential of jkx times a periodic function is called the Bloch theorem. You can see the name in the first line of the page, the Bloch theorem. It's a very important theorem because since the exponential term is given, okay, there is nothing to find about it. It is already prescribed, okay? Obviously, what we shall do is solving for u. So the new unknown of the problem is this new function u of k, okay? But this function is periodic. This means that it is sufficient to find this function only in one period. We shall not anymore calculate the solution at each x in the lattice, because once we have found it in one period, we know it everywhere else. Okay? Now, what are the conditions to be imposed on this periodic function? Well, this periodic function forms the solution. So it has the same continuity as W. Okay, so for sure, if we, I go back for a second to the figure, okay, if we solve the Schrödinger equation in one period, for instance, starting at 0 and ending up at a plus b, okay, the conditions to be imposed are that in the middle, at the point A here, the solution must be continuous with a continuous derivative, okay? And then we must impose the periodicity of u, that is, the value of u in the origin here must be equal, because of periodicity, to the value at a plus b. And similarly, the value of the derivative at 0 must be equal to the value of the derivative at a plus b. Okay, so we have 4 conditions to be imposed, and we shall be able to use only one period of the function in order to fully solve the problem of the Schrödinger equation. Now, in order to proceed, since we know the form of the solution, we take separately the form of the Schrödinger equation that applies where the potential is 0 minus second derivative of w equal to a alpha squared w. And then we take the other expression and we replace w with the product u times the exponential, okay? Obviously, when we do so, we have a Schrödinger equation in which each term in the equation is multiplied by the exponential, so we can delete the exponential, and we obtain 2 equations that are the equations for u. Instead of solving for w, we now have to solve for u, but they are still equations that you can see here. In the intervals in which the potential energy is 0, we have second derivative of u plus 2j k u prime minus some constant k squared minus alpha squared times u of k equal to 0. So this is a second order differential equation in one dimension with constant coefficients. In the other interval, in which v is equal to v0, we have an equation that is slightly different, but of the same type. Okay, we have again a second order equation with constant coefficients, What is changed is just that we have k squared plus beta squared in the parentheses, okay? You remember that with this type of equation, we proceed in the solution by considering the algebraic equations that are associated to them, okay? So we consider the second degree equations of the that are associated to these two differential equations. And we find the solutions, the zeros of the algebraic equations. And these two zeros are quite easily found, okay? For the first equation, the two zeros, after some manipulations, turn out to be purely imaginary. We have minus jk plus or minus j alpha. So these are the two solutions of the algebraic equations that apply where v is equal to 0. Instead, in the intervals where v is equal to v0, the solutions of the second algebraic equation associated to the second differential equation are s equal to minus jk plus or minus beta, so they are complex solutions, okay? Then you remember the solutions of the differential equations are obtained by taking the exponentials involving these roots, okay, and considering linear combinations of these exponentials with undetermined coefficients. So let's call uk plus the solution in where v is equal to 0, okay? So such that we have to use the first form of s. uk plus is a linear combination in which the undetermined coefficients are c1 and c2 of the exponentials that you can see here. So we can plug into the first exponential, we select alpha with the plus, so we have exponential of j alpha minus k x. And in the other one, we plug the other solution, that is the one in which alpha has the minus. So we have exponential of minus j alpha plus k x. For the intervals in which v is equal to v0, we call the solution uk minus, and it is another linear combination whose coefficients in this case are c3 and c4 of the exponentials with the second form of s. So we have exponential of beta minus jk x or exponential of minus beta plus jkx, okay? So these are the solutions, and we have 4 undetermined coefficients, okay? You are already accustomed to the counting of the unknowns. We have 4 unknown coefficients, C1, C2, C3, and C4. But we have 4 conditions because we have the continuity of the solutions at x equal to a, and then we have the periodicity, okay? So we have 4 conditions and 4 unknowns. However, we are not able to find the 4 unknowns because the algebraic system is homogeneous, okay? So as usual, we shall be able to find the ratio of 3 of the 4 parameters, C1, C2, C3, and C4 with respect to the fourth. Okay? And we shall not be able to find the last parameter because if you remember the form of the potential energy, the particle can be found everywhere in the lattice, okay? And because of that, the solution is not normalizable. I go back for a second to the figure because if you consider the figure, you see immediately that this is a succession of barriers. So at each barrier, we may have a tunnel effect. The particle may tunnel across any of these barriers, so there is a probability to find a particle on either side of each of the barriers, okay? But this applies to any barrier. So in conclusion, the particle can be found anywhere inside the lattice, okay? And this is the reason why the wave function cannot be normalized, because we must integrate over infinity, okay? So the wave function is not normalizable in this case. Now we have to impose the continuity. We do it in the origin. I'm still on the figure, okay? So we may impose the continuity here instead of imposing the continuity at A, okay? So we impose the continuity at 0, that is easier, because all the exponents become 0, okay? So we impose the continuity of the function and the first derivative at 0. And then we impose the periodicity over a period that goes from minus b here to plus a. It is just the same period, a plus b, okay? So it is more convenient to find a period across the origin, okay? So the first condition is relatively easy because we are in the origin. So we impose that UK plus at 0 be equal to UK minus at 0, but this obviously provides C1 plus C2 equal to C3 plus C4. You simply let x equal to 0 in the exponents, and then you find this, okay? The other condition is that you impose the continuity of the derivative in the origin. So you have the derivative of UK plus at 0 must be equal to the derivative of UK minus at 0. The derivative is for UK plus, the derivative is in the first term you multiply by j alpha minus k. And in the second term you multiply by minus j alpha minus jk. Then in the expression of UK minus, if you take the derivative, you have a factor beta minus jk. And finally, you have a factor minus beta minus jk, okay? You see immediately, then you have a jk factor everywhere. So you have jk with the minus multiplying C1, minus jk multiplying C2, minus jk multiplying C3, and minus jk multiplying C4. 4, but C1 plus C2 , is equal to C3 plus C4 due to the first continuity condition. So if you multiply by minus jk, you have still an identity. So you cancel all the terms involving jk from the second equation, okay? And you are left with a relatively simple equation that is J alpha C1 minus C2 must be equal to beta C3 minus C4, okay? From this, you immediately extract C1 and C2 as a function of C3 and C4, okay? And you find the two expressions on the bottom line of the page in which you have compacted the coefficient 1 minus j beta over alpha, you call it 2 sigma, okay? It is a complex number, and the relation that provides C1 and C2 in terms of C3 and C4 are here, okay? This is the easy part of the calculation. The other part is a little bit more boring because we are not in the origin anymore. So I'm simply going to skip it because it is not exciting as a calculation, but it is relatively easy. What we do, I go back to the figure, we consider the solution at x equal to a, okay, of course we consider the solution u plus, okay, because we reach the limit with u plus and we reach point A. And then we go on the left of the origin and we consider u minus and we reach the point minus B. And the function, because of periodicity, must be the same in these 2 points, okay? So we impose that uk plus at A must be equal to uk minus at minus B. And then we do the same for the derivative, okay? Again, we find a relation between the coefficients C1, 2, 3, and 4, okay? But what are the other parameters involved in this calculation? Some parameters are given because, for instance, A and B are given because they belong to the structure, so we know A and B, okay? V0 also is given because it is the value of the potential energy when it is high, okay? So there are still 2 parameters in the equations that are the total energy of the electron and the value of parameter K. Okay, so when we solve and then we impose the continuity of the function and the derivative, essentially at the very end of the calculation, we find a relation between alpha. Remember, alpha is the square root of the energy. Beta, that is the square root of V0 minus the energy, and K. So the important point to be understood is that when we solve for the coefficients C1, C3, C4, and C1, 2, 3, and 4, okay, we are solving an algebraic system, and the algebraic system is here, is visible on the page, okay? All those quantities K, L, A, B, etc. are given, are parameters that contain energy and K, okay? And the unknowns parameters are C3 and C4. So we have a 2 by 2 algebraic system to be solved, but this algebraic system is homogeneous. So you remember that in order to solve the homogeneous system, we must impose that the determinant of the coefficients is 0. Okay? And by imposing that the determinant of the coefficients is 0, we find a relation between alpha, beta, k, etc., between the parameters that are involved in the problem. Okay? So the determinant, I read it for you, has one term is the coefficient of C3 in the first equation. So it is sigma parenthesis 1 minus capital KL over AB. The second one is C star parenthesis 1 minus BKL over A, etc., etc. So we impose that this determinant vanishes. When we do so, it takes a long calculation, but it is not complicated, simply long. We find this expression, the expression that is visible on the second line. So I read it for you. It is beta squared minus alpha squared divided 2 alpha beta. This multiplies the sine of alpha A and the hyperbolic sine of beta B plus cosine of alpha A times hyperbolic cosine of beta B. This is equal to the cosine of k times A plus B. Remember that A and B are structural parameters. They are simply the period of the lattice. So they are given everywhere. When you see A and B, they are given. Alpha and beta depend on energy, but not on the k vector. So the left-hand side of this equation, as in many places alpha and beta, it is substantially a complicated function of energy. On the other hand, the right-hand side of the equation is the cosine of k alpha plus beta. Alpha plus beta is given. So it is essentially a function of k. So in a short notation, we may call the left-hand side f of e, some function, some complicated function of e, okay? And the right-hand side is g of k. G is the cosine of k times a plus b, okay? So if we succeed in inverting this relation, and we shall see how to do it later in the second hour, we eventually obtain E of k. You remember that k multiplied by h bar is the expectation value of momentum. So eventually we are able to find the relation between energy and momentum from this calculation. Okay? So the issue is to find the relation between E and K by manipulating the expression above, okay? Of course, there is nothing to do analytically because it is relatively complicated, okay? But we have 1 minute left. We can check two properties, okay? The left-hand side depends on E. The right-hand side depends on K, and it depends through the cosine. You remember that the cosine is even with respect to the argument. So if you replace K with minus K, the right-hand side does not change, of course, because the cosine is even. That means that the energy is an even relation of energy, of momentum. Okay, which is always true also in classical mechanics. You remember, energy is always even with respect to momentum. The second issue is that if you, at the right hand side of the relation, if you replace k with k plus 2 pi over a plus b, that is one Brillouin zone, obviously due to the periodicity of the cosine, nothing changes. So that means that the left-hand side is invariant if we add to k one full period that is given by the Brillouin zone. So this is also important. Due to the periodicity of the direct lattice, the eigenvalue of the problem, that is the energy, is periodic in the reciprocal scale lattice. We shall come back to this later, but now we stop for 10 minutes and we shall meet again in 10 minutes. Okay. So you remember we were considering this relation here that is in the middle of the page. This relation is somewhat complicated, but it is able to provide us with a relation between energy and K. That is exactly the object of the calculation of the solution of the Schrödinger equation independent of time. That is providing the eigenvalues of energy. We have noted that due to the properties of the cosine, the relation between energy and K is even. So it is invariant if we replace K with minus K. And also that E is periodic with respect to K, and the period is the Brillouin zone, okay? You may start connecting with some information that I gave you when we were talking about the semiconductor bands, okay? Remember that we were considering the relation between energy and K in a crystal, and we notice that the relation is made of several branches of a function that are called the bands, okay? At this point, we have not reached the concept of bands yet in this calculation. We are not there. We shall be there in a minute, okay? But we are not arrived at the bands. But at least we have understood that energy is even and periodic with respect to K. And you remember the figures of the bands that I showed you in one dimension. They are symmetric from left to right. That is, they are even. And also they are shown only within the first Brillouin zone, because you remember we said they are periodic, so it is useless to consider them outside the Brillouin zone because of periodicity, okay? Now the issue is the expression in the middle of the page is still rather complicated from for an analytical analysis, but we can improve it a little bit by making this observation. You remember that we have two parameters that are beta and alpha. So if you go back to the definitions here, you see that alpha is proportional to the square root of energy. So it is independent of V0. Instead, beta is proportional to the square root of V0 minus E, okay? So we may try to simplify the expressions by taking the barriers higher and higher. That means we go to the limit in which V0 becomes very large. If in which V0 becomes very large, if that happens, then beta also becomes very large. And essentially it becomes a function of V0 only, because if V0 goes to infinity, it becomes dominant, of course, with respect to the energy. So we can neglect the energy in the expression of beta, okay? So we may try to see what happens if we take V0 larger and larger, okay? Obviously, we simplify something. Also, we notice that beta becomes dominant with respect to alpha if we take V0 and make it to grow to infinity, okay? But if we just let V0 go to infinity, we make the barriers higher and higher, and we kill the tunnel effect. Okay, we reduce the crystal to a succession of boxes with infinitely high sides, okay, and there will be no tunnel effect anymore. The particle will stay, the electron will stay in one and only one of the boxes where the initial conditions place it, okay? So going to infinity with V0 is too much. But we observed when we were considering the tunnel effect that the tunnel effect becomes more and more difficult if the height of the barrel increases. But it becomes easier if the width of the barrel decreases, okay? In this case, the width of the barrel is B, okay? So we may try this manipulation. We increase V0, but at the same time we decrease B, the width of the barrel, so that the probability of tunneling does not change. Okay, so we simply deform the form of the barriers, but we do not touch the probability of tunneling. Okay, and in the equation this is visible very easily. If we increase V0 and decrease B in a way that makes the product B times V0 equal to some constant, then nothing changes. Okay, so we go to the limit in a very special form. We increase V0 and we decrease B while keeping the product equal to a constant. Okay, what happens if we do so? Well, first of all, we already noticed that beta becomes dominant with respect to alpha. Okay, so in this factor, beta squared minus alpha squared divided 2 alpha beta, alpha squared can becomes negligible. We neglect it. Okay, so this parameter here becomes beta squared over 2 alpha beta. Okay, for the moment we don't cancel beta square and beta, we leave them. Then, since B is going to 0, in such a way that the product B times V0 is a constant, you notice that when V0 becomes very large, beta becomes proportional to the square root of V0. Okay? So V0 is proportional to the square of beta. So the prescription that V0 times beta must be a constant is equivalent to beta squared times B must be a constant. Okay? But if this product is a constant, the product beta without the square times B goes to 0, because beta is proportional to the square root of V0, so it is weaker than V0. So beta squared B stays a constant, beta B goes to 0. And you remember, when the argument of the hyperbolic sign becomes very small, then the hyperbolic sign becomes equal to the argument itself. So hyperbolic sign of beta B tends in the limit to beta B. So this is why in this expression here you see beta B. At the same time, in the second summand, you have hyperbolic cosine of beta B. And when beta B becomes small, the hyperbolic cosine tends to 1, apart second order terms. Okay, so we replace the hyperbolic cosine with 1. So only cosine of alpha A is left. And at the second, at the right hand side, A plus B becomes A because B goes to 0. Okay. Then at this point, we can eliminate the beta in the denominator with the beta here in the numerator. And then we bring B here near beta squared. So we have beta squared B that tends to a constant. Okay. So in conclusion, by this manipulation, we have simplified enough the relation. It is in the next page. Okay. When we go to the limit, we have, you remember, in front of the sign, we have sine alpha A times beta square B divided by 2 alpha. We may multiply by A. A is a constant, it depends only on the structure, so we can safely multiply by A. So in conclusion, we have sine of alpha A over alpha A times a parameter that we call theta. It is the limit of AB beta squared divided by 2, okay? And this is it. Theta, of course, is strictly positive, okay? And this is the simplified form of the relation between energy and K, in which, again, K is only in the right-hand side, and the energy is hidden only inside alpha. Because you remember, energy is alpha is equal to the square root of 2m times the energy divided by h bar. Okay, so this is a simplified form of this relation. We shall analyze it in a minute. Okay, but before we do it, we can say that we could try to solve this equation graphically, because instead of calculating the relation E of K, we may calculate the relation K of E, the inverse relation, okay? So we may fix K, and when we fix K, we, of course, impose a value to the right-hand side. So we fix K. Cosine of Ka becomes a number. And of course, this number is between 1 and -1, because we have the cosine. And then we check all the possible values of alpha, and we see whether the left-hand side becomes equal to the right-hand side. Okay? For instance, we can try to see what happens when the energy goes to 0, when we are at the bottom of the lower band. When the energy goes to 0, alpha goes to 0. Okay, because alpha is proportional to the square root of the energy. So when alpha goes to 0, the cosine goes to 1. And sine of alpha A over alpha A also goes to 1. Okay, so the left-hand side has a value at 0 that is 1 plus theta. Okay, and this is also the value, the minimum value of energy, because E cannot be smaller than 0, you remember. Okay, then what do we expect when we start from the energy equal to 0 and increase the energy? Well, when we increase the energy, we increase alpha. So, of course, the cosine of alpha A oscillates. and also the sign of alpha A oscillates. Okay, but the sign of alpha A is divided by alpha A, and alpha increases because we are increasing the energy. So the ratio sine alpha A over alpha A becomes less and less important as the energy increases. Okay? So when the energy becomes very large, we eventually have that only the cosine of alpha A is left. This other term is negligible. And eventually, if the cosine of alpha A is equal to the cosine of Ka, that means that alpha is equal to K, which is exactly the expression of the relation between energy and momentum of a free particle, which is reasonable. If the energy becomes very large, then the effect of the potential energy will become smaller and smaller and less important, okay? So for very large energies, we expect that the particle will behave almost as a free particle, so that the relation between energy and momentum will be almost equal to that of the free particle. Okay, so let's see how the solution can be found graphically. I say it again, we fix K, find the value of the right-hand side, and then we find the possible values of alpha such that the left-hand side becomes equal to the right-hand side. And this can be easily made graphically. The horizontal axis is alpha A. So it is proportional to the square root of energy. When energy is 0, we are in the origin, okay? So this value of the curve that is on the top is theta plus 1, okay? So theta in itself is, you see, it's 15. This is 21 in this scale, so theta is equal to 20. Okay. Then the lower horizontal line, thin line here, is -1. So this is the lower boundary of the cosine of Ka. The upper thin horizontal line is the upper value of the cosine. It is +1. So the cosine must be somewhere in the middle. Let's take a value of the cosine that is this thick dashed line, okay? The intersections, that is the possible solutions of the energy for this given K. When we give K, we give cosine of Ka, okay? So for this given K, the solutions are the intercepts. So we have one solution here, another, 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 another. You see that these curves keeps oscillating, but it becomes more and more similar to the cosine because the sine of alpha A over alpha A disappears when alpha becomes very large. Okay, so this curve will oscillate forever. We may increase the energy as much as we please. We'll always find solutions. Okay, so for one given K, we have infinite possible values of energy. Then we change K, so it is like we move the horizontal dashed thick line up or down, okay? So we find another set of intercepts and so on and so on and so on. So by this graphic solution, we find all the possible eigenvalues of energy, and we see that for each k we have infinite possible values. For each k we have infinite possible values of the energy, okay? Can we also extract the existence of the bands? Well, of course we can, because there is another figure that is better suited to show this. This one. Okay, this is a portion of the previous figure. Okay, so we have this function that oscillates. It is the left-hand side. Okay, when this function is larger than 1, that is here or here or here, etc., etc. And when this function is smaller than -1, like here or here, it is impossible to find a solution because the right-hand side is the cosine. The cosine can never be larger than 1 or smaller than -1. So the intervals in which the oscillating function is either larger than 1 or smaller than -1 are intervals of energy in which we do not have any possible solution. They are the forbidden bands. Instead, the intervals of energy, in this case the abscissa is alpha A, but it is proportional to the square root of energy. The intervals of energy in which the oscillating left-hand side is in between 1 and -1 are the intervals in which we can find the intercepts so that they are the allowed bands. Okay, in fact, in this figure you see the strips marked as allowed bands on top and the other strips that are marked as forbidden bands. Okay, so there is an alternation of allowed and forbidden bands. So this model that is oversimplified but still able to capture all the important features of the physical issues tells us that one, we have infinite bands, an alternation of infinite allowed bands and infinite forbidden bands. That the energy is even with respect to k, and that the energy is periodic with respect to k with the periodicity equal to the Brillouin zone. So actually it is able to describe well the general features of the relation between energy and momentum. Of course, when we calculate the bands from this model, they are not similar to the actual bands that we can calculate numerically that are much more complicated. Okay, but in any case, this model is very useful. The model has a name. It is called the Koenig and Penny model, as you can see in the figure. Okay, so this is the Koenig and Penny model. Oops, sorry. Okay, one more point. In this analysis, we have considered K as a continuous variable, okay? When we impose the periodic boundary conditions, remember K becomes discrete, okay? But all this model is applicable anyhow, okay? So it doesn't really matter whether K is continuous or discrete. All the results that we have found stay, okay? One may ask, what if we consider a really finite crystal, okay? If we consider a really finite crystal with no periodic boundary conditions, but with real boundaries, that is, the crystal finishes at some point, okay? We must solve the Schrödinger equation in this more realistic case. We cannot use the block functions anymore, okay, because the block functions apply only if the structure is periodic, okay? But anyhow, we can solve the Schrödinger equation with some little more difficulty, not that much, okay? And we see that in any case, the band structure is there, okay? So the band structure is present even if we avoid the use of the periodic boundary conditions and the block functions, okay? Actually, the number of periods of a crystal that is necessary to form the energy band is not very large. About 10 periods are sufficient to form a band structure, okay? And this is a calculation that can be done relatively with relatively little effort, okay, still in one dimension. I think that I must change the pages. Yes, because what follows is the three-dimensional replica of it. So now you should be able to see a page entitled Comments on the Koenig-Penny model. This material will be uploaded into the website, okay? So it is just a continuation of what I was saying earlier. Here we can start again with this function and see how we can calculate in practice the shape of the bands using the Koenig and Penny model, okay? The first observation is this. Obviously, we must confine ourselves to the case in which the right-hand side of equation 9.1 is between -1 and 1, okay? If we don't, if we impose that the right-hand side is larger than 1 or smaller than -1, of course we can do it, but then we go into the complex field because the cosine becomes something that is complex, okay? So we still can do the calculation, but we don't find the bands anymore. Also, it is convenient to change the variable. So instead of using alpha A, we use a variable that it is called U. U is equal to alpha A divided by 2, okay? And of course it is non-negative because the parameter alpha is proportional to the square root of energy, okay? So when we replace the variable alpha A with 1/2 U, okay, we can manipulate the equation number 9.1, and we can impose that this equation has the left-hand side that is between -1 and 1. Okay, so essentially this prescription splits the equation into two equations, okay, separately, two separate conditions. Okay, one condition is that we must have the right-hand side larger than -1. And the other condition is that the left-hand side, sorry, must be smaller or equal to +1. Okay, so we split the problem into two inequalities. And after an easy calculation, we find equations 9.4. What is the meaning? The meaning is that U is proportional to alpha, so it is the square root of energy, okay? 2 times U over theta, theta is the limit, you remember, that we have at the left-hand side, is the limit of B beta squared times alpha divided by 2. So this must be larger than minus the tangent of U, and at the same time it must be larger than the cotangent of U. Okay, so if we try to represent graphically these conditions, we find a figure that shows immediately why we have the bands. This is the figure, okay? So the blue line is two over theta times U. You remember, U is proportional to alpha and alpha starts from 0. So this is a function of U that is simply linear. It is a straight line with an angular coefficient that is 2 over theta. So this straight line is the blue line. Okay? Then the blue line must be larger at the same time, because these two conditions here must be fulfilled at the same time, must be larger than minus the tangent of U and also larger than the cotangent of U. So we simply draw minus the tangent So minus the tangent is the red line, is the set of the red lines. And plus the cotangent is the set of the black lines, okay? So the graphical solution tells you that the allowed bands are in the intervals of U in which the blue line is simultaneously above both the red and black line. So this happens here in this interval marked with A. Okay, you see that the blue line in this between 0 and 1/2 pi, the blue line is above the black line and also above the red line. Okay. Instead, if we go near the origin, the blue line is still above the red line, but it is below the black line. So we don't have solutions here. So the extension of the horizontal extension of this arrow marked with A is the extension of the first band in the units of U. Then we must transform it in the units of energy, but in the units of U, this is the first band. The second band again must be such that the blue line is above the red line and the black line. Okay, so in this case the blue line is always above the black line, but not always above the red line. It is above the red line only in the extent marked with B, the arrows indicated with B. Okay, you see the second band is a little bit wider than the first band. Okay, etc., etc. So by this construction we can find the extension of the bands. We see that the allowed bands increase in size when the energy increases, and the forbidden bands decrease in size. The description of the band is very easily, because consider this equation. Okay, cosine of Ka equal to some function of energy. If you take the inverse function of the cosine, that is the arc cosine, you can make K explicit. So you have K is equal to 1 over A times the arc cosine of the left-hand side. So you can explicitly find K as a function of energy. Then you simply rotate the axis by 90 degrees and you see the figure E as a function of K. And this is exactly what was done for this. This is the first band. It was a calculation in which first it was calculated K as a function of E. And then the axes were rotated in order to provide E as a function of K. Actually, this is some normalized energy. And here, instead of K, there is K times A. The Brillouin zone goes from the vertical line marking. Of course, it is minus pi in this scale, okay? And the other edge of the Brillouin zone is pi, okay? If you want to calculate the second band, you have this figure. So this is the first band, the same as before. It is a little bit more compressed in order to provide room for the second band, okay? Then, if you draw the second band inside the Brillouin zone, you find a red curve, okay? You remember silicon, okay? You see some resemblance, no silicon, sorry, gallium arsenide, okay? So the red curve is the second allowed band of this example of the Krennigan-Penny model when we restrict the consideration to the first Brillouin zone. The first Brillouin zone is between the vertical line here, the magenta colored here, and the magenta colored line here. Of course, it is pi and minus pi in this scale, okay? On the other hand, we may also decide to provide a different representation. We may fold the second band in order to stay in the second Brillouin zone. So the second Brillouin zone is outside the first Brillouin zone. So the second Brillouin zone is in between the magenta and the orange line here and also on the other side. So it is between pi and 2 pi. So if we swap the red curves outside, we obtain the green curves, okay? You see that if you try to connect the green curve with the black curve, you obtain sort of parabola, okay? So it is not equal, but similar to what you have in free space, okay? It is a deformed parabola with a gap. And the forbidden gap is, of course, the region in which there are no curves, that is in between the two horizontal blue lines, okay? So in this very simple model allows you to calculate in one dimension an approximate form of the bands. We of course could continue with the third, fourth, and whatever band as we please. A final observation is the following. Since we have an analytical description of the band, we could also calculate the effective mass. You remember, the effective mass is proportional to the inverse of the second derivative of the energy with respect to K. Okay, so for instance, we are not going to do it, but it is very easily done. We can calculate the second derivative, you remember, and then we, by some manipulation, we extract the effective mass of the particle in which that is subjected to this E of K relation. We can also do another thing. You remember that in this analysis, A is the period of the lattice in one dimension. We started with the period that used to be A plus B. But then we took the limit in which B goes to 0. So the period is A. Okay, so the barriers are infinitely high and infinitely thin. Okay. You remember the mechanical sensors, of course, okay? And you remember that the piezoelectric effect. These effects are effects that are due to the mechanical deformations to which the material is subjected, okay? And you remember that the mechanical deformation change some conduction parameters, okay? So in this case, it is very easy because we may recalculate simply the bands after changing the value of A, because if we stretch the one-dimensional lattice, we make A to increase. And if we compress the lattice, we make A to decrease. Okay, so we may simply check what happens if we change the value of A. Of course, it is not so simple because A is on both sides. Okay, so the calculation is a little bit involved. Okay, but yet it can be done. And at some point, we have a result of a calculation here. This is it. In which the calculation was repeated, so the Koenig and Penny model was used again and again, using a different value of the parameter alpha. Of course, this parameter is the lattice constant, is the interatomic distance in this simplified model. So these curves have been drawn by considering A equal to 0.6 nanometers or 0.5 nanometers or 0.4 nanometers, and this is the lowest band. Okay, so you see obviously that since the Brillouin zone is equal to 2 pi over A, when you increase A, so when you go from the blue to the black to the red case, the Brillouin zone decreases, becomes smaller. Okay, the Brillouin zone is marked by the vertical lines in this figure. Okay, but also you see that the band shifts upwards or downwards depending on the value of A. So if you increase A, so if you are stretching the material in this example, the band goes down, okay? But you remember that in equilibrium, the filling of the band is imposed by the relative position of the minimum of the band and the Fermi level, okay? So it is likely that this stretch will, by changing the position of the minimum, will also change the filling of the band. Okay, so we may have more electrons or less or fewer electrons in the same band, so the conduction of the band will also be affected. Okay. Another thing that will be affected is the group velocity. Okay, you remember that the group velocity is the derivative of E with respect to K, so obviously if you deform the band, you change the group velocity. Okay, so all these calculations are possible thanks to this very simple model. Okay, of course, in realistic cases, we must do it more carefully, but this concludes the part of the class that is in quotes exercises. Okay, I shall upload part of this material into the website. And from tomorrow we shall restart with the material that is the bulk of what is expected to be material for the exam. Okay, so we now stop. There are 2 minutes left. Some of you are registered tomorrow morning. The exam will not start tomorrow morning because there is a superposition of commitments. The exam, for those that are interested, will be taken next week. Okay, I shall send a message to the students that are in the list. Okay, so we close here for the moment. Thank you, and we shall continue tomorrow.